Hello, physics class. Today we're going to be going over conservation of momentum in a two-dimensional collision. For an example of conservation of momentum, that says that directly before and directly after a collision occurs, the impulse j equals 0, which by the impulse momentum theorem says that the change in momentum also equals 0. This just means that the sum of the final momentums minus the sum of the initial momentums must equal 0. Therefore, the sum of the final momentums must equal the sum of the initial momentums. And since this is a two-dimensional collision, essentially what must be true is the change in momentum on the x-axis as well as along the y-axis must both add up to 0. As an example, let's say right before a collision happens, there is a 5 kilogram mass labeled A that is moving directly to the right at an initial velocity of 10 meters per second, or positive 10 meters per second. And then there is an object B of 4 kilograms that is initially at rest with with a velocity of 0 meters per second. After they collide, mass A goes 30 degrees above the x-axis in the right and upward direction, and mass B goes 45 degrees below that axis to the right and down. Well, if we have the starting masses and the angles of approach and collision, then we can determine two unknowns, which is the final velocity of object A and object B. Now, to do this, we really need to solve for the momentum in both the x and y direction. It doesn't matter which one we start with. So let's just say we start with the condition that the change in momentum along the x-axis must be 0. Therefore, the final momentums in the x direction must equal the initial momentums. Momentum is just mass times the velocity that mass is currently traveling at. So, breaking up our equation further, the final momentum side is the mass of object A times the final velocity of object A in the x direction, plus the mass of object B times its final velocity of B in the x direction, must equal the mass of object A times its initial velocity in the x direction, plus the mass of object B times its initial velocity in the x direction. Now, what are these final velocities A of x? Well, that's just the x component of that velocity vector. That can be changed into the total magnitude Vf of A or Vf of B multiplied by cosine of their angle of redirection after collision. So that breaks up our equation into the mass of object A times its total final velocity times cosine of 30 degrees as it reflected by 30 degrees plus the mass of object B times its final velocity times cosine of 45 degrees. And that is going to be set equal to the mass of object A times its initial velocity plus the mass of object B times 0. Here's the nuance for this particular type of problem. Initially, object A, all of its velocity is just in the x direction. Therefore, its initial velocity's x component is that positive 10 meters per second. Object B is at rest, therefore it has 0 velocity in the x direction. And for objects A and B, the x component of their final velocities are both to the right or they're both positive. That's why right now our fourth line of our code is as it is. So That allows us to have the initial velocity of B just drop out to 0. Thus, its initial momentum is 0. And the initial momentum of object A is just its mass times that positive 10 meters per second. Therefore, our next line of code, just bringing some knowns together, we have our final velocity of A times find cosine of 30 plus the final velocity of B times 4 cosine of 45 degrees equals 5 kilograms times positive 10 meters per second. Simplifying these, cosine of 30 degrees, that's just square root of 3 over 2. Cosine of 45 is just square root of 2 over 2. Therefore, these simplify to the final velocity of A multiplied by 5 square root of 3 over 2 plus the final velocity of B times 2 square root of 2 equals 50 kilograms meters per second. Now, this gives us one equation with two unknowns, which means we can't determine exactly what either unknown is unless we had a second equation. That's why, if you didn't already start with solving in the y direction, we can now solve for momentum in the y direction with the condition that those sums of the momentums, the change must equal 0. Therefore, the final momentums in the y direction must equal the initial momentums in the y direction. Breaking everything apart, that's still just the mass of object A times the final velocity's y component plus the mass of object B times the final velocity's y component plus the mass of object A times its initial velocity's y component plus the mass of object B times its initial velocity's y component. Now, what we need to look back is, in our starting problem, object A's final velocity has a positive y component because it's upward. Object B's final velocity has a negative y component because it is downward. Object A's initial velocity is only in the x direction, therefore its initial velocity in the y direction is 0. And because object B was initially at rest, just like its x component of velocity, its y component will also be 0. So what that gives us is the mass of A times its total final velocity, sine of 30 degrees, plus the mass of object B times its total final velocity, times sine of 45 degrees, times -1, because it's actually pointed downwards, because the y component of velocity is pointed downwards for object B. All that must equal the mass of A times 0, because its initial velocity was only in the x direction, it had no y component, plus the mass of object B times 0, because it was at rest, therefore it had no y component to its velocity initially. Breaking things down, that's the final velocity of A times 5 sine of 30 degrees minus the final velocity of B times 4 sine of 45 degrees equals 0 kilograms meters per second. Just adding the negative part to the other side, we have the final velocity of A, 5 sine of 30 equals the final velocity of B, 4 sine of 45 degrees. We can easily solve for one unknown in terms of the other. Doesn't matter which one you do, but if we solve for the final velocity of A, it is equal to the final velocity of B times 4 sine of 45 degrees divided by the product of 5 sine of 30, which just simplifies to 4 square root of 2 over 5. Or if you are not as comfortable with simplifying trigonometric functions, just give a decimal equivalent of 4 square root of 3 over 5 to maybe 5 decimal points just to be safe. Now at this point we have two equations and two unknowns. The final velocity of A times 5 square root of 3 over 2 plus the final velocity of B, 2 square root of 2 equals 50, and that the final velocity of A is equivalent to the final velocity of B times 4 square root of 2 over 5. Well, to solve for one of our variables, we can just replace into one equation what we determined one of those variables to be with respect to the other unknown. And I shouldn't call these variables, they are unknowns. So if we know what VF of A equals with respect to VF of B, in our first equation, let's just change the final velocity of A to final velocity of B times 4 square root 2 over 5. Therefore, that becomes final velocity of B times 4 square root 2 over 5 times 5 square root 3 over 2 plus final velocity of B times 2 square root 2 equals 50. We now have one equation with one unknown. It's now possible to solve for that unknown. Solving for that unknown, essentially simplifying things. What we have on the right half, there's 5 in the numerator and 5 in the denominator. They cancel out, and 4 divided by 2 would just be 2. That leaves final velocity of B times 2 square root 2 square root 3 plus final velocity of B 2 square root 2 equals 50. Now, when you have multiple things raised to the same power, like 2 raised to the 1/2 or square root times 3 raised to the 1/2 over the square root of 3, you just multiply those two numbers together and keep them to the same power. So 2 square root 2 square root of 3 becomes 2 times the square root of 6 plus 2 square root of 2. Essentially, since both of those were multiplied by VF of B, we can pull that out and put everything else in parentheses and then set that equal to 50. Therefore, the final velocity of B is exactly equal to 50 divided by the sum of 2 square root of 6 plus 2 square root of 2, which is about 6.5 meters per second. Really 6.47, round it to 2 decimal places for problems like these, or 3. Continuing on, the final velocity of B is approximately, just to give ourselves an extra decimal point, 6.47 meters per second. What can we do with that information? Well, we just solved for the final velocity of B. When we were solving the change in momentum in the y direction condition, we found an equation that sets VF of A equal to VF of B times some ratio. Well, if we plug in the exact value for VF of B, the final velocity of A equaling 50 divided by the sum of 2 square root of 6 plus 2 square root of 2, all multiplied by the ratio of 4 square root of 2 divided by 5. Just factoring out some common things, that becomes 50 over 5 times 4 square root of 2 over 2 square root of 2 times square root of 3 plus 1. This is just for those who are more comfortable with modifying algebraic equations. It's not necessary, but if we do that, that simplifies things to 50 divided by 5 is 10. 2 square root of 2 over 4 square root of 2 over 2 square root of 2 becomes 2. 10 times 2 is 20 in our numerator. That leaves square root of 3 plus 1 in the denominator. Therefore, the exact velocity of A after it collides will be, or immediately after it collides, is 20 over the square root of 3 plus 1, or approximately 7.32 meters per second. Now, if you weren't comfortable with factoring out common factors to simplify our algebraic equation, you could just take the approximate answer for the final velocity of B, 6.47 meters per second, plug that into the equation VF of A equals VF of B times 4 square root of 2 over 5. Therefore, the final velocity of A is approximately 6.47 multiplied by 4 square root of 2 over 5, which comes out to about 7.3199, or about 7.32 meters per second. So for the final answers, we got final velocity of B is approximately 6.5 or 6.47 meters per second, and the final velocity of A came out to about 3. 7.32 meters per second, or their equivalent values of irrational ratios. But you're welcome to simplify to use approximate values up to a few decimal places to solve for the other unknown, just for lecture. In any case, that's just a little explanation on conservation of momentum, starting with the impulse momentum theorem, in order to solve an example problem in two-dimensional collisions, where we know all the necessary information of angle of impact to angle of reflection or retrajectory, and the initial velocities, allowing us to solve for the final velocities after collision. So, around the 16-minute mark, thanks for being part of this lecture. Hope it clicks, and if not, we can discuss it later. In any case, peace.